All right, let's talk about the homework. We'll get into section 10.2. All right, one thing I need to kind of review from yesterday. Looking back, I know we went over it, but there's a couple things when it comes to the tangents that I don't know that I took long enough to discuss. So I want to make sure we review this. There's two things going on here. One question is, how many times do the circles cross? Okay, that's called intersection. All right, so in our notes yesterday, we would have called these intersection points. The circles intersect twice. These circles intersect 0 times, and we wrote that in our notes, okay? Now, when it comes to, intersection, the second type of question you're going to be asked are about tangents, all right? There are two types of tangents. There are internal and external. And we didn't draw them in on every example yesterday, but let's do that right now. So on these ones, are there any internal tangents? For number 8? No. But there are 2 external tangents. All right. Now I want to do one like number 7. This was not in the homework, I know. But I want to show you what it looks like. So here is number 7, something like this. All right. How many intersection points do these circles have? 0. Be careful with how many tangents you draw in. Okay. I bet everybody sees the 2 external tangents. Do you agree? Do you see any internal tangents? A lot of people don't see them. And we don't always, yesterday I didn't draw in every tangent. But here's what the internal tangents would look like. Can you see that? I mean, imagine that only touches once. And then that one. So this one has 4 tangents, 2 internal, 2 external. Okay? So a quick little rule, if you want to get real technical about it. If you were to draw a line connecting their centers, anything that crosses through that line would be called an internal tangent. You see how the blue lines cross through that purple line? Internal tangents. Don't cross through it, external tangents. Now, what if the circles just touch once? They would have how many external? 2. How many internal? 1. Good. It would go up and down, right? It would just touch the circles right where they cross. Are you with me? So I want to clear up that vocabulary today. Make sure that makes sense. All right. Now, the homework. I heard some people asking about 26 or 28, wasn't it? 28? All right. I bet we all set these equal. 2x plus 5 equals 3x squared plus 2x minus 7. 2 tangents to the same circle are always congruent if you break them up into segments where they intersect. The 2 segments are congruent. All right, well, we're going to solve for x. So we're going to subtract 2x from both sides. We get 5 equals 3x squared minus 7. Some of you are saying, I don't remember how to factor a quadratic. You don't have to, okay? Because the x terms cancel out, this would be a binomial. Okay, 2 terms. If I don't want to do it, but if I subtracted 5 over, I would get 3x squared minus 12. Do you agree? 3x squared minus 12 equals 0. There's no x term. That's not a trinomial. We have to unfoil it. This is one where I'm not going to factor. I'm actually just going to add 7. Divide by 3. And square root. What number could have been squared to give you 4? 2 and negative 2. So we call that plus or minus 2. Now, I want to draw your attention to something because we've glossed over it for a while. And I'll tell you why. Mr. Westfall, we did a bunch of Pythagorean theorems. 3 squared plus 4 squared equals x squared. 9 plus 16 is 25. Why didn't we write plus or minus here? Plus or minus 5. Why did we ignore the plus or minus for that chapter, Preston?
Because the hypotenuse has to be larger than the other side.
Yeah, and a side length can't be negative, can it? That side length can't be negative 5 units. Because it was applied to triangles, we didn't write the plus or minus. Technically, every time, I guess I could have written plus or minus and say, oh, sides can't be negative. Just do the positive. Maybe that's the safe way to do it. But you guys are bright. I bet you could figure out in this context, can x be negative? Careful. What's 2 times negative 2? 2 times, this is 2 and negative 2. Let's test this one. Ready? What's 2 times negative 2? Negative 4 plus 5. That's okay. What's negative 2 squared? Times 3. Keep 12 in your mind for a second. 12. 2 times negative 2. Negative 4. 12 minus 4. Minus 1. Or minus 7. That's okay. So does negative 2 work in this context? Does positive 2 work in this context? Both 2 and negative 2 work. Right triangles? Can't have a negative side. This context, it's fine. So be careful. Be careful. The rest of your math career, when you uncover a square, depending on the context, you're going to allow for a 2 and a negative 2. Because a lot of times it's on a graph. They're going to be parabolas on a graph. And you're going to want the negative and the positive. Okay? Right triangles, we don't take the negatives, just the positives. Other homework questions you'd like to discuss? Page
14.
Sure. The question, was it about whether it's a tangent? Yeah, okay. Paige, were you good with that segment right there is 8?
Yeah.
Okay. What's this called from here to here? Yeah, a radius. It's a radius, right?
Yeah.
We could call it x. We actually don't need to call it x. What is that length?
Is it
It's the same as this length. It's a radius.
8?
So that one is 12. And so the hypotenuse is 20. So is 12 squared plus 16 squared equal to 20 squared? So they're going to do that a lot this chapter. They're going to draw in radii and say, are they going to recognize that every radius in a circle is congruent? Okay? It's a common theme. Other homework questions? All right. 10.2 is called finding arc measures. Where in real life have we heard the word arc in that context? What's that? Arc marks, yeah. For angles. What about in real life? Like not outside, so outside of math class.
Like in a house.
In a house? Like where?
In like a doorway or something.
Yeah, the word arch and arc kind of go hand in hand. Where else do we hear the word arc? That's a different arc. So the can. Come on, no basketball players in here? No basketball players. 3-pointer?
Oh, Ryan's a basketball player.
3-pointer? Yeah. Yeah.
Yeah.
All right. We're going to be we're building off of this concept the whole chapter. So this is called an arc right here. This is an arc, okay? An arc is an unbroken part of a circle consisting of 2 points called endpoints. and all the points on the circle between them. A central angle. What do we hear in that word central? We hear the word center, don't we?
Yeah.
A central angle is an angle that's formed at the center of the circle. The vertex is the center of the circle. It's right here. So today's lesson is going to have to do a lot with the angle and the arc. Angle and the arc. Did we have the conversation in this class about what a degree is? Not yet? Okay, bless you. I think this is sometimes something we gloss over, and students work with it but never quite understand it. So we're going to talk about that. We're going to build on that today. I need to do it quickly so we don't run out of time. Does anybody know what a degree is? Back up. Does anybody know what a foot is? It's a unit of measure, and we know we work with it every day. It is, you describe it to someone as 12 inches, right? It's got a measurement. You all know what that is. How about a degree? It's also a unit of measure. What is it? Okay, could you show me 90 degrees? Could you show me 180 degrees? Could you show me 270 and 360, right? 360. What's 1 degree? 1 degree is 1/360th of a way around the circle. I bet you would agree with that, right? 1 degree, it's a small little sliver. It's 1/360th of a circle. Do we get that? Now, angles can be measured in degrees, and arcs can be measured in degrees. We're going to find out today. The angle in degrees and the arc in degrees, if it's a central angle, are the same. So what does that angle up there look like at the center of the circle, the one I highlighted in green? Maybe 100 degrees, would you say? I can't tell from here. Is it close to 90? Maybe a little bit more? So the yellow arc would also be around 100 degrees. Does it look like this arc has gone 100 degrees out of the 360 around the circle? Yeah, that seems reasonable, right? Now, tell me if you can hear the difference. This is extremely important that you get the difference. Students always confuse this. What if I walk around a circular pond? And I talk to someone afterwards, they're like, oh, I went on a really nice walk around this pond. I go, oh yeah, how far did you walk? I didn't quite go around the whole pond. I went like 100 degrees. Is that impressive? Okay, what if I told them I went 360 degrees around the circle? Is that impressive? Around the circular pond? Pretty impressive? Spoiler, the pond was only this big, okay? All right, watch.
That was a great accomplishment.
You're impressed, aren't you? 360 degrees doesn't tell you anything about how far. It doesn't tell you anything about length, does it? So there's arc that's measured in degrees, and then there's arc that's measured in length. Oh, I just walked around a 10,000 foot pond. Like the circumference was 10,000 feet. Okay. Well, almost a couple miles. That's all right. Right? Do you see the difference? One's arc length, one's a measure in degrees. So what's a degree? It's a measure, it's a portion of the distance you've gone around a circle. I need to be careful. Not a portion of the distance. It's a portion of the rotation of the circle. And arc length is talking about distance. Do we get the difference? Awesome. Okay, moving on. Today we're talking about angles and arcs, though, not length yet. So a minor arc is measured with degrees, and it's labeled by its endpoints. Does everybody see this arc symbol right here? AC. The M out front means measure of, and the little arc above it means arc. So the measure of arc AC, and I told you it's the same as the measure of the angle at the center of the circle. They're both x degrees. And for that one, we might say, maybe an example would be 60 degrees for that central angle. So what would its arc be? If the angle ABC is 60 degrees, what's the arc? More than one person. 60 degrees. How do you know? Oh, look, it said they're equal up here. The arc and the angle are equal. A major arc is an arc whose points are on or in the exterior of the central angle. So everything outside of it. So I'm going to highlight these for you because it might be hard to see. This was the minor arc. This is the major arc. It's everything outside of that minor arc. In a special case, if the arc touches the endpoints of a diameter, we call it a semicircle, right? We call it a semicircle. And the arc would be 180 degrees because we've gone around half the circle. What do you notice about how we name a major arc? Scott, what, Caden? 3 points, very good. Any ideas why that might be, or you want to pass it off to someone else?
If there was only two, it'd be the minor arc.
Yeah, we wouldn't know which way to go. We'd probably go the shortest distance because that's just how we work, right? If I said, "Oh, everybody up there, look at arc AC," you would go the shortest path from A to C. But if I said arc ADC, now you have to go in order from A, pass through D, then to C. Anybody need more time on that? All right. And a quick little note. Well, we talked about that. All right, find the measure of each arc of circle P, where RT is a diameter. Make sure you note that RT is a diameter. Okay? These are like little puzzles. Some of you are going to like them if you're a little nerdy and enjoy math. All right. You may want to highlight the arc you're finding. If I go from R to S, I have to go the shortest distance from R to S. Do you agree? I don't have a choice to go the other way around, or else it would be called a major arc. Tally?
I have a question about the last slide.
Sure.
I don't really understand the equations they wrote in.
I think it might make more sense if we do this application, okay? So, do you agree this is arc RS? Tyler? I just highlighted arc RS. Yes? So, two things we need to point out. Arc RS, or the measure of angle, RPS. Does everybody agree? angle RPS is the angle that connects the arc. Do you all see that? Be honest. Do you see it? Because the angle has two sides. Its endpoints are the endpoints of arc RS. And on the last slide tally, we said the angle, the central angle equals the arc. So on this picture, the measure of angle RPS equals the measure of arc RS. So that angle equals the arc RS.
So that's just always true.
For a central angle. So if this angle is 110 degrees, what's this arc? 110 degrees. Is everybody good with that? All right, now when someone asks, is that always true? You guys are smart enough to figure this out. Let's play a little imaginary game, okay? Let's keep R and S, the endpoints of the arc. What happens if I move the angle back this way? What if I move the angle back this way? And then back again and keep R and S. What's happening to this angle? It's getting smaller. Do you all see it? The farther I move the vertex away, the smaller the angle's getting. That's not for today. That's a future section. For today, we're keeping that angle at the center. Center, same angle, same arc. Okay? Move it back, and we'll have to do some more calculations. All right, next one. Arc RTS. Which way do I go? Clockwise or counterclockwise? RTS. Counterclockwise, because I have to go from R. My next one I have to hit is T. R, then T, then S. R, then T, then S. Oh, well, that's everything else in the circle except for the 110. 360 minus 110. We don't need a calculator for that one, do we? If you can take away 100, you can take away 10 more. What's 360 minus 100? 260 minus 10 more. Did you get 250? 250 degrees. Now, what about RST? R, here's the blue one. RST. Careful. RST. What's RT called again? What's segment RT called? A diameter. It splits a circle in half. What's the measure of arc RST? 180. Half of the circle. Not so bad, right? All right, adjacent arcs are arcs that they're next to each other, just like adjacent angles are next to each other. Arcs that have a common endpoint. All right, what are those 40, 80, and 110? Are those central angles or are those the arcs? Central angles. Good news. They're the same as the arcs. Okay. So if angle GRH is 40, then arc GH is 40. Okay. So let's start off with GE. Arc GE goes from G to E clockwise or to E counterclockwise? I heard clockwise. I agree. If it's named with 2 letters, you have to go the closest path. Now, I will warn you. Some books, some problems will call this, they could call it arc GHE. It's the same arc, it's just more specific. You understand that? GE is the same as GHE. It's going the same direction. All right, GE is, it's an arc, but good news, if these angles are 40 and 80, what's the arc? 120. 120 degrees. All right, GEF. GEF. Ella, what'd you get for that one?
230 degrees.
I got. You guys get 230 degrees? It's 120 to E, and then 110 more. So 230 degrees. How about arc GF? All right, GF. Clockwise, counterclockwise. Counterclockwise, good. What do you think GF is? 130. Isn't it?
130.
Yeah, isn't it everything not that wasn't the 230? Right, 230 was from G all the way to F. And this is the rest of the circle. So 360 minus 230 is 130. Make sense? GF, we just did that one. Next. We're not going to have time to discuss. I apologize. But we're going to have to just talk about this one. What do you notice is different about this picture? They're percents, aren't they? Those are all in percents. What should all of those percents add up to, do you think? 100, not 360. 100%. Okay? So A to C. All right, A is here. C is here. Counterclockwise or clockwise? Clockwise. It's named with 2 letters. We have to go the shortest path. So what percent of the circle does that take up? 38%. Okay. So that's 38% of the circle. We're asked, what's the measure of the arc in degrees? Well, isn't it 38% of 360? Isn't it 38% of 360? It's 38% of the whole circle. So 38% is 0.38 times 360. 38%, 0.38 times 360. I'm getting 136.8 degrees. 136.8 degrees. So that arc took up 136.8 degrees of the circle. 38%, which is the same as 136.8% degrees. All right, ACD. ACD. Okay, it's what we just found, 38% plus another 23%. We're up to how many percent now? Hold on a second.
61.
61, I think, right? 38 and 23. So 61%. 0.61 times 360. 0.61 times 360. Did you get 219.6 degrees? And you're going to miss points if you leave off the units of measure here. This one's degrees. Okay. If you just don't put anything there, I'm not going to know whether you knew it's percent or degrees. That's kind of part of the problem. So you have to know that, right? 61% of the circle is 219.6 degrees. All right. Congruent circles theorem. Guess what? All circles need to be congruent is to have the same radius or diameter, right? That's all that they are defined as. A circle has its radius. Scroll down a little bit. So in a same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding central angles are congruent. All right, good. All right, tell whether the indicated arcs are congruent. Are RS and TU congruent? So here's what you guys should be doing. If you're doing a homework problem, you're like, I can't remember that. Go back to this theorem, okay? We're not talking about whether the circles are congruent, okay? In the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding central angles are congruent, okay? All right. Start with that one over there. Start with letter B. All right, give a reason. We're going to get into arc lengths soon. We'll talk about the length of the arcs here in just a bit. All right, we're starting with letter B. We'll do letter A together. All right, what do these tick marks mean for the radii? They're congruent. If the radii are congruent, the circles are congruent. And because these central angles are both 95 degrees, then are UV and YZ congruent? Are the arcs congruent? Yes. Yes. And you could say by the congruent central angles theorem. By the congruent central angles theorem. Now, be careful there. We need to read this again. This gets confused a bit. In the same circle or in congruent circles. Do you see the requirement there? I'm going to read it again. In the same circle or in congruent circles. So we had to show that those circles were congruent first before we could say the arcs were congruent. Are you with me? Okay. Now, another part that I want to make sure was clear, and this was my pond example, okay? If this is 95 degrees, what's this arc? 95 degrees. If this is 95 degrees, what's this arc? But is that the length of the arc? Because when we say congruent, we're talking about the length of the arc. That's not the length of the arc. That's the measure of the degrees of the arc. Do you agree? Okay. On to this one. Our circle is, now I guess we'd both call these both circle Q. But is circle Q with radius S, or QS, congruent to circle Q with radius QU? No, they're not congruent. Are these arcs both 90? Yes, but are they congruent arcs? No. Think about it. If you are walking around this pond and you walk from R to S, you're not walking the same distance as if you walk around this pond from T to U. Do you all understand that? That's a farther distance. It's a greater distance. Why? Because the circles weren't congruent. All right? So, not congruent. The measures of the arcs are both 90. The measures of the arcs are both 90 in degrees, but the lengths of the arcs are not. Do you understand that in the context of walking around a circular pond? Okay. All right, we're gonna have to. This will be our last slide for today, and it does have a proof. It's not that bad. Okay. All circles are similar. Well, that's kind of obvious, right? They're all the same shape, but they're not all necessarily the same size. So here's the idea, and I'm just going to have to lead you to this concept. Do you remember way back when we showed that polygons were congruent by mapping one onto another with a set of rigid motions? Oh, reflect this across the y-axis and then translate it down 2 and right 3. Remember that?
Yeah.
A dilation was only to keep it similar, proportional, right? So here's the goal. How can we map circle C onto circle D? I bet you would say, if it was on a graph, move it over this many units and up this many units. Okay? Now, how do we show it's similar? Well, map C onto D, it might be a rigid motion, but it's going to definitely involve a scale factor. Do you agree? We're going to have to use a scale factor to enlarge C to turn it into D. Do you remember how to find a scale factor? Was it new divided by original or original divided by new? New divided by original. So what do I need to multiply this radius by to get that? S divided by R. Right? If this was 5 and this is 2, 5 divided by 2. You'd multiply this circle by to get that one. In general, S divided by R. Does that make sense? So you would translate it over and up and then multiply by a scale factor of S over R. All right, that's just the kind of the general idea there. If it's on a graph, it's a little bit easier. You would translate circle O to the right A units and up B units, and then S over R dilation. All right. We're going to have a review day tomorrow where we practice these topics from 10.1 and 10.2. So make sure you do the homework. We'll go over it. We'll review tomorrow. You have an extra long weekend. More time to do more homework, right?
No.
I'll take that as a yes. Josh, I expect that from certain people.
Look, man, I'm sorry that you got that bad.